density function can be anything. It could be increasing, it could be decreasing. Let me actually do this kind of realistic for the Earth. I have this density function that I'm going to give you, and it's an approximate density function of the Earth. We know for the Earth and a lot of other planets, the dense material falls to the center. So usually the density decreases as you get farther out. You get denser material in the center. So the density of the Earth looks like this. Here's the density function. Rho is 14.2 minus 11.6 R over R times 10 to the third kilogram per meter cubed. So when the little r is equal to big R, the density is equal to, subtract that, you get what? 2.6, roughly about 2.6. So that gives you 2.6 times 10 to the third kilogram per meter cube, which is equivalent to about 2.6 gram per centimeter cube. So it's about 2.6 times as dense as water, which is about the density of rock, the density of rock at the crust of the Earth. Okay. And if the little r is equal to 0, then the density is equal to, well, just 14.2. So it has iron there, nickel there, a lot of dense material, more metallic substances down at the core. And plus another thing is you have all the gravity of the Earth that's pushing in on the core, and it compresses the core even more and makes it even more dense. That's why it's this high, 14.2 times 10 to the third. So how would the gravity change? Well, we would expect, if you come to the graph here, we would expect that if you go halfway, you wouldn't, because the material here is more dense, it wouldn't have dropped to 4.9. Maybe the graph should look something like this now. I'm just predicting. Kind of like that. So if you go halfway to the Earth, the gravity should be more than 4.9 because it shouldn't have decreased that much. Because if you go halfway to the Earth, right, there's still a lot of mass there. There's the core of the Earth, okay? So the gravity, the little g there should be greater than 4.9. So once we do calculate the answer, we should get something greater than 4.9. So let's do the answer, let's do the actual formal math here. G is equal to Gm enclosed over R squared. You always start that way. Then you say G over R squared integral rho dV. And then here is where you put the rho function. You integrate from 0 to little r. Because the reason you integrate from 0 to little r and not big R is because we want to know how much mass is enclosed in that gravitational Gaussian surface of where you are at. So you do that. Now we need to put the dV, the volume of a spherical shell. Okay? The volume of a spherical shell, which is 4 pi r squared dr. And remember, once we're done with the answer, then we're going to check to see if it's continuous. We're going to do the continuity check. So the 4 pi comes out of the integral, and of course 10 to the third, there's a 10 to the third, that comes out. So we're left with here what? Let's continue with up here. Okay, so you know what, let me erase this too. Yeah, so G over R squared, the 4 pi comes out, we're left with integral 0 to r, 14.2 times r squared minus 11.6 r cubed over big R, dr. Right? And that's the radius of the Earth. So now you go 4 pi g over r squared. You integrate that 14.2 r cubed over 3 minus 11.6 over r to the 4th over 4, and then 0 to r is just itself. Okay? And now I need a 10 to the 3rd there, right, somewhere. Can go inside of the parentheses because this and this are both the little r. Okay? It can go inside the parentheses, and now this is going to make this equal to r. It's going to make this equal to r squared. Okay? And now we could check to see, you know what would be nice to, because the answer is in terms of g, 4 pi, and 10 to the 3rd, it would be nice to write down here, in other words, it would be nice if we could have the answer in terms of the gravity on the surface, okay? Because we know the gravity on the surface, the little g is equal to, on the surface, gm over r squared, right? So what I could do, and this is the actual mass of the planet, right? So at the surface it's equal to gm, the total mass of the planet over r squared. So I could write g as equal to gs r squared over m, okay? And then this one is going to equal what? This big G I can now write as g of the surface r squared over m times 4 pi let's divide this to 14.2 divided by 3. Well, it's going to be 4.73 continuing. R minus 11.6 divided by 4, 2.9. R squared over R times 10 to the 3rd. Okay, so so it would be nice here to even make one more change. Here's what I'm going to do. I'm going to make this multiply this by r, so I'll make this a cube, and then I'll divide this by r, and I'll divide this by r, so that my final answer is in terms of the ratio of my little r to big R. See, so I made this r cubed, I added 1 r here, and I divided this by r. So now, look how I'm going to do this. This is actually the average density of the Earth, the mass of the Earth, divided by, I can make this here, so G is equal to, look here now, Gs divided by, this is the mass, divided by, if you divide this mass by the 4 pi r cubed, bring that down here, okay, and then divide by 3b, so that this 3 then can go up. I have mass over the volume, that's the density of the Earth, right, mass over volume, and then this 3 is there to cancel this, and then this one I could write